So now I'm going to show you another physics which we have added to our model, that is solid mechanics. This is our solid mechanics study. The whole geometry is linear elastic material. It's all boundaries are with fixed constraints. And another thing that I would like to add, that when we select this study of solid mechanics, we have to add the Young's modulus and Poisson's ratio for the materials used in our geometry. So this is our seed basically, and on the seed our solid mechanics does not apply, since this is of our deforming domain with the moving mesh. Yes, this is our thermal strain for the source, Young's modulus and Poisson's ratio. We are not using or applying solid mechanics on the seed since it is in our deforming domain that wise. And this is our argon gas. For this, the Poisson's ratio and Young's modulus is 0, since this is the gas region, not a solid region. And this is graphite. Its Young's modulus is mentioned here, Poisson's ratio is assigned. So yes, that's it. So now I am going to show you the numerical simulation of the transport of gas species in the physical vapor transport growth of silicon crystal. So we are working on a 2D asymmetrical model. Starting with the geometry, I am going to show the steps I have performed using COMSOL Multiphysics. So this is our geometry. The crucible wall, that is basically the outer region that acts as a insulator as well, of width 300 mm and height of 400 mm. The seeds silicon source, that is placed over here, of dimension 250 mm by 50 mm height. The vapor gap, this is basically the region for the vapor gap, which I will discuss later as well. That is also of 250 mm of 250 mm dimension. And this is our seed crystal over here. This region is for the seed. I will show you later on when I will show you the material mode. And this is the this is also of 250 mm and 220 mm height. And this is our top insulation. Top insulation in order to prevent heat from escaping. And moving towards the materials, this is the seed, like I have discussed earlier, silicon carbide. This is the source. This is of the same material. This is also of silicon carbide. All of their physical properties are mentioned here. You can go through the values. And this is our argon gas region, that is the vapor gas region, which in which we will show you the transport of diluted species as well. And this is our graphite material, the outer wall or the boundary that will act as an insulator. Moving towards the moving mesh. Now moving towards the study. There are 3 types of studies that we have involved. Number 1, moving mesh. Number 2, heat transfer in solids. And number 3, transport of diluted species. Moving mesh is basically used in cases when you have to show the deformed geometry, the change in the geometry with the passage of time, or like in our case, we are studying on the growth of silicon crystal. So we have added this study, and this moving mesh deforming domain is only selected for the seed region. All the other region is constrained and fixed with 0 displacement. And this is the fixed boundaries. These are the normal displacement, normal mesh velocity, as prescribed earlier. This now moving towards the heat transfer in solids. This is our solid region. Like I have discussed earlier, this is a crucible wall. Only this region is for the vacuum region, in which we will add argon gas and will show you transport of diluted species. You will see the streamlines of the vapor moving upward in the coming study. The initial values is 22273.15 Kelvin, and the initial temperature that is selected for the source. Thermal insulations. This is temperature 1, that is the start of the temperature, which is 2500 Kelvin, and temperature 2, that is the temperature of the seed crystal. This is our thermal insulation. All the walls are thermally insulated in order to prevent heat to escape. Now moving towards our next study, that is transport of diluted species. This region, likewise I have discussed it earlier, that this is our vacuum region, in which we will add an argon gas as a material. This is an axial symmetry. This is the source flux through which the heat will be generated and will produce vapors. These are some fluxes which we have to add. These are their values. Moving towards the mesh. For this geometry we have selected extra fine mesh in order to obtain accurate results. So I have selected the element size to extra fine, and now come towards the study. We have selected time dependent study, as its the change will occur with the passage of time. For this we have to select time dependent study, and I am going to show you the heat transfer as well as the concentration of the model. This is our surface temperature. Basically the heat is generated through this part and will move upward, passing through the argon gas, and will reach towards the seed. This is our concentration module. You can see these are the formation of vapors towards the seed, and you can see the temperature controllers very well. I will show you the animation at the end. This is the cross-sectional model for our geometry, in which we can see the thermal gradients and the heat transfer. Moving towards the animation, I am showing you the heat transfer. You can see that how efficiently the heat is being transferred towards the seed. This is the temperature line, which will show you the temperature values, and this animation will show you the mass transport of vapor generation through the argon gas region, and these are the vapors. This is the heat source. You can see all the boundary walls are fixed with zero displacement and zero heat emission. So yes, that's it. This is our complete model. Thank you.